This conference will now be recorded.
Okay, we're at 12.
Morning, Bappy. Morning, everyone.
Hey, David, how are you?
Good.
Well, Rita, we should probably get started.
Okay.
Elko's here. Elko's our trigger.
Okay. Can you guys see my screen?
Yeah. Yep. Looks great.
Okay. Wonderful. Good morning, everyone. I just wanted to maybe spend the next 20 minutes to 30 minutes, depending on the level of questions, to just paint a picture of what I envision would be an ideal EDA tool environment setup for a multi-die system integration in a package. And there are many phases in this development. It could be anywhere from exploration phase, design, optimization, validation, analysis, all the way to the point that the user is getting ready to sign off and go to production, effectively release the design for production. So let's see if I can make this one work. Okay. So I've done a little bit of animation trying to paint this picture, what's happening, what I feel the dynamics in the market are driving the need for this multi-die integration in the package. And as you're aware, as our semiconductor densities, the transistor densities are continuing to grow exponentially from each node to a next generation advanced silicon technology node, features and capabilities of many devices in a system are being integrated within a larger device because you can do so much more higher levels of integration. But an increased need for integration is causing these densities to grow and make these devices even larger, which is great, especially for the new technologies, new market spaces, such as the fast-growing artificial intelligence market, which demands a lot of high computing. In order to meet this need, especially in terms of the electrical bandwidth, the higher performance, the lower latency, we see an increased need of bringing the memory much closer, which you guys are all very aware of that. So we see a lot of new integrations of the high bandwidth memory with the computing processor in the same system. And of course, as the demand grows in terms of the performance and higher levels of integration, we see more and more devices being integrated, more features and capabilities within the same SoC, and of course, more additional memory integration. But as these die sizes are growing, their yields are growing much smaller, lower percentages. As a result, it makes these devices much costlier and harder to manufacture, excuse me. And of course, with the smaller technology nodes, we are approaching a much more expensive technologies to deal with. And a lot of the complexities, because of the increase of complexities in these larger devices, and also, of course, the smaller technology nodes are bringing more complexities in terms of designed methodologies or new parasitics that needs to be dealt with. Of course, the verification part of these smaller technology node devices are going up also, addition with their design cycle times, because it takes longer to verify them. So the design cycles are getting longer and longer. So the manufacturers are having a hard time designing these complex systems and yet be able to get them to the market as fast as possible. So because of the die size yield problem that I mentioned, we see a lot of die disaggregation happening where the larger die is broken into a smaller die, and which adds more complexity to the design within the package in this case. Historically, we've seen system designers, SoC designers, signal integrity, power integrity, thermal integrity designers, of course, the package designers and PC board designers collaborating in creating this system, all the way from the chip level design definition, the system level, and integration on the board. But because these systems are getting more complex, historically these individual disciplines used to work independent of each other to some extent with very little overlap. But because of these design cycles are getting longer and also the complexity is getting increased, there is a need for a closer collaboration by all these different disciplines. You can no longer start sequentially designing your SoCs and then decide on what you're going to do, put them in a package all together with a bunch of other devices, or individually package it. That's why we see a lot of co-development happening. So that requires a platform that enables all these different disciplines to collaborate at the same time and be able to provide feedback, not just at the early exploration phase, but also throughout the design process. As you're designing your die-to-die connections, you want to be able to provide feedback to your SoC design to tell them if it would be more optimal to put a microbump in certain location or the certain spacing or pitches versus that traditionally would have been placed with respect to the I/O, or where you would put your macros within the SoC and be able to get the most optimal die-to-die interconnect. Similarly, where you put your C4 bumps or the copper pillar bumps with respect to the other devices to be able to get the most optimal package substrate design, where these structures are getting connected to the package substrate to be able to get the best escape routes to minimize the number of the package substrate layers to get the most optimal pricing and also better performance. So we are talking about quite a complex system. And as we talked about die disaggregation, by the way, we have not identified any EDA tools that are available in the market that actually caters to die disaggregation gracefully. But besides that, as we are disaggregating these larger SoCs to smaller SoCs, would somebody mind going mute? There's a background noise. We are requiring more interconnect. So as we integrate higher levels of high bandwidth memory in the package, we do need making connection between the memory chips and the computing chips that are actually driving them. And of course, with the die disaggregation, you need interconnect connecting the different processing units together. That calls for different types of PHY that would be required to be implemented to make those connections. Some of them could be parallel, such as the high bandwidth memory or the interconnect, high bandwidth interconnect, HBMs and HBIs, or they could be differential, serializer, deserializer types, such as the ultra short reach or extra short reach USRs or other SerDes that are available in the market. And of course, every package requires IOs to go off package. That could be anywhere from parallel interfaces or to the serial interfaces and any ranges of the data rate. Now, in order to make the decision, there are many different options in the market available. As you may be aware, within OCP, we have been defining the BO interface, the HBI interface, and also there have been a lot of discussion in enabling other IO interfaces by providing a wrapper that would enable connection to different protocols or enablement with different type of electrical interfaces that any of these die-to-die devices could benefit from. But overall, if you would want to bucketize these type of interfaces, there are two major types. There's a parallel interface, and of course, there's a serial interface. And a parallel interface has dedicated memory type of parallel interfaces that are mainly defined by JEDEC, the HBMs, the generation 2s and 2Es, and the 3.1 that is on the verge of being released more broadly. And of course, there's parallel interfaces that are for non-memory interconnect, such as connecting CPUs to CPUs or processor units to memory devices of different non-DRAM based.
Could I ask a question on this slide? Are you taking questions, John?
Go for it.
Yeah, just for a clarification, on the serial, you've got obviously latency is high, interconnect reach is long. Obviously, if we decided to do, extremely short reach is not long reach, and if we can turn off back and we can turn off other DSP features because the link is so short on a transceiver, could the latency be low and the interconnect reach be short? And therefore, so my analysis so far, when I did a presentation on Tuesday at Open Power about the open memory interface, which is just a slow 25 gig transceiver interface, and 8 lanes of that times 8 channels, it actually takes up the same amount of die area as an HBM. And so, and not only that, obviously you don't have the packaging problems because you can go to a lower density. So my question, my challenge is actually the extremely short transceivers could compete with the bunch of wires or the AIB approach potentially, and then we could have just one standard like TTL in the old days. So that's really my. I'm just challenging whether those 2 points there.
Sure. Let me get to that point if you don't mind. Yes, I was going to get to that phase. So there's some definitely advantages and disadvantages. So it's not trying to promote one or the other. I was trying to explain based on the advantage and disadvantages. It's very high level, general, and I explain why I have defined SerDes as a higher latency. There are choices, and there are different needs in the system. And based on those needs, either they're through getting bandwidth with minimum interconnect, wire connection between the devices, or optimizing latency or cost. I mean, we have a lot of factors, knobs to turn. In general, the parallel interfaces require thousands of interconnects. The HBM itself is over 1,000. And of course, we are talking about BOWs and HBIs, which could be anywhere from minimum of 30 wires interconnect signals, mainly. Of course, you have additionally power signals that go along with them to over 2,000 interconnect. Now, SerDes, as you pointed out, requires very few differential pair. Pretty much, you could get almost the equivalent of the 1,000 wires of a parallel interface, which is 4 wires connected with the same throughput. Now, in the SerDes part, you require to go from a parallel interface, which typically your core is designed in, to a serial.
Right.
And then you communicate across the line, and then you convert back to parallel. That's the latency, conversion from parallel to serial. Can you avoid that in this particular solution that you were mentioning? I don't think so. There is a latency. Yes, you can optimize that, but that's the added latency that does not exist in a parallel world. You effectively are processing within your core, and you're spitting out the parallel interface information across the link to the other device. So that's why my definition of latency is.
Would it be good to define that? Because obviously, if you're trying to drive a really long link, then there's a tremendous amount of DSP. and a tremendous amount of forward error correction and the like. So that adds huge amounts of latency. But
Oh, well,
if you really
yes.
have an extremely short reach and you're just going from a muxin from parallel to serial, sure, it's going to be higher latency. But are we talking a few tens of picoseconds or 100 nanoseconds, or so what we should define that before we say that it's a killer or not, if you see what I mean.
I am no means saying it's a killer. All I'm saying is if you had to apple-to-apple comparison at the high level, it would be low and high. And as you pointed out, a PCIe Gen 3, Gen 4 doesn't need a FEC.
Right.
So that negates yes. Okay. If you're talking about 50 gig, 100 gig,
does 112?
You would need a. Yeah, I'm not.
Hey guys, I'm sorry. I hate to break up a discussion. Just today,
Sorry.
I apologize.
No problem.
So yes, so it's really the full range of going anywhere from 1 gig to 50s and 100s. By no means I'm breaking down and focusing on the higher speed ones, but in general, going back to what I was trying to explain is because of the number of the interconnect that the parallel interface requires, effectively, it would drive to a need for a much denser capability in terms of routability. So that points out to the silicon interposer. And then, of course, the serial not needing that many wire interconnect that would be able to cater to a much less denser environment, but still, depending on the wires and the number of devices you're integrating in a package, you would need different levels of density, but maybe not as dense as the silicon interposer would provide, but still. But one thing that would be a killer for the higher speeds, especially when you go to the 50s and 100s, it's the low resistance. Whereas the impedance of the silicon interposer would kill you in the higher speeds, even with the small die-to-die connections that you would be able to accommodate. So then fan out comes into play for the most part. Again, this is my view of what I have seen and based on my understanding of what's happening. And there may be potentially more technologies advanced out there that would enable this. So overall, at the very high level, there's some advantages in the number of links and latencies. Again, very general. And of course, depending on your design type, and how long your connections are from die to die. By putting a die right facing to another die, it's easy to make short connections. But when you have many devices in your package and you have to make a lot of routes that are not just directly within few millimeters of each other, then you're talking about more longer traces that are needed. And that's where the SerDes come into more attractive. Historically, the packaging world, we've been able to provide a solution for a single die and also to some extent multi-die integration in a package using the same organic or different types of packaging substrate. Now, the technologies used for implementing these types of packages, they tend to be on a lower density routing. I mean, the smallest cutting edge spacing and width of the traces are about 0.8 micron as far as I have been able to find out. Sorry, not 8.8, but 8 micron width and spacing. Whereas in a semiconductor world, we're looking at much finer traces. And that's the reason we see this window of opportunity between the packaging substrates of today as a generic monolithic packaging compared to what silicon can provide. And that's why we see the introduction of the silicon interposer coming into market more and more, trying to fill up that gap spacing for the application that needs more of a denser in terms of the number of wiring that needs to be connected between devices. And of course, the packaging world is also bringing in along their fan-out version, which is more of a packaging approach by bringing this RDL-based routing that is not as fine-grained as the silicon interposer base, but still much smaller width and spacing as the traditional organic substrate packages are offering today. So there are, if I would categorize them, I can be challenged by there are a lot more types of packaging solution out there, but if I could just bucket them into three major devices, structures, technologies, I would break them down in a traditional multi-chip module, MCMs, that are typically today built off of the organic substrate. This is being the very light green layers on the bottom of these structures. And of course, the die-to-die connections are happening within the package substrate. But then that itself, as I mentioned, it's got some limitations in terms of the width and spacing in these devices. You cannot go anything smaller to some extent, more broader acceptance or capabilities within the market. But it allows you to go long traces. It's very attractive for traditional connections, and especially if you don't need a whole lot of wiring densities within a package. And of course, traditionally compared to other new technologies such as silicon interposers or even fan out, that tends to be a much lower overall packaging cost solution in terms of substrate design. Then you look at the wafer level fan out that brings the density of wiring a little bit better. It allows you to go as smaller width and spacing as 2 micron. That allows you still reasonable distances between the die connections, but at the same time, the price tends to be a little bit higher. And also it has its own little bit limitations compared to, but again, it provides a medium solution that is not able to be provided by the MCM world. And of course, silicon interposers provided.
RDL material, the material for the RDL on that?
So these are the RDL materials. These are post-fab. So these are not the silicon-based RDLs. These are the polymer-based RDLs, or the RDLs that are done after dies are already sliced and put in a carrier. Okay. These are not your traditional semiconductor level RDLs that is done as a fab process of the silicon is done. Is that the question?
Yeah, I was just, it's not silicon, it's a polymer.
Yes.
Yeah.
And it's post-fab. So your silicon manufacturing, your CMOS device SoCs is already done. And then you put this layer down on top of it. Okay. So again, for the benefit of time, there are benefits, again, like the different type solution, 5 solutions that I was mentioning. The packaging options have also a lot of different options. If you need high density, and if you are using HBIs, HBMs, the parallel interfaces that need a lot of density, the silicon interposers tend to be your most optimal option out there in the market. At the same time, it's not the only option. You could also use the fan out for that matter. You may not get as high densities as the silicon interposer offers, but the fan out is the next best. And of course, the MCM is there, but then it does not allow you to get the spacing and the traces that you need in the amount of spaces. So it makes your package substrate much larger if your width and spaces are larger than it needs to be with the other options. And of course, there are other things to consider, such as the trace losses, and also definitely the cost to some extent can be the major driver in decision making. But again, the question is, what is more important to you? Do you need to get the device out? Do you have a lot of time to design this? And what type of solution would best fit the needs that you have today? Now, by making all these devices in a package, by putting them all together, it adds a lot of complexities. It adds signal quality issues because you have thousands and thousands of wires going either between memory and the processing units in a parallel form or the serial form. So signal integrity definitely is one of the categories that needs to be really closely evaluated at the package level between a die, how the signals are going. And of course, as you put in more devices in a package, thermal and power adds up. And that brings heat, and it brings the heat also, not that it impacts the performance of the devices within every one of these chips, but also it can bring mechanical stress in your package substrate. And of course, by adding all these different constraints within your package, it's making it a very complex environment that a traditional package design tool is not capable of adding all these capabilities and consideration into place in one environment. And of course, as I pointed out, there is a need for package and chip co-design at the same time for the most optimal solution. What is happening in today's EDA world? So the focus was going to be for the EDA tools. So what is happening? What I see is there is a lot of disjointed solution in the market today. And what I mean by disjointed, we have one tool may be used for planning. One tool is used for implementation of wiring, connecting between die to die. One tool is used for extraction. One tool is used for validation. One tool may be used for analysis and simulation. So a lot of these EDA tools don't have the same interface. You cannot move smoothly without translation from one interface to another interface, from one platform to another platform. As a result, especially when you're doing with signal integrity, power integrity, sequentially as you're designing, then you find out you have an issue, then you have to go back in a drawing board. And as a result, then you realize that, uh-oh, I have to go and make some more edits, which makes your large feedback loops in order to get to convergence and to optimize them. And a lot of these tools also do not have automation, which makes it even harder. Imagine connecting those thousands of connections manually. It's impossible, especially as you're adding 2s and 4s and 8s and even more number of HBM devices, or partition your die much finer grains to get the best performance capabilities within that. And of course, it's not just the signal routing. You have the power and ground routing. You have the shielding that you need to be considering, especially with the dense environment of the HBMs and HBI. So in order to be able to provide an environment, ideally, a unified environment that you can do all your explorations, planning, designing, analysis, all in the same environment, that minimizes a lot of movement from one tool to another tool. And also by bringing in a lot of automation, bringing an environment that is DRC aware, it's aware of the rules, that when you're making wire connection, you know already you're making a mistake, so you don't make it, or especially when it's automated, it would just follow the rules that you are feeding it. It would be ideal. It would minimize the number of iterations and your design cycles. What we are seeing is with a lot of these automation, you can go from months of development to few days of development. It's huge. You have more time for analysis. And of course, a lot of these tools are historically done or optimized for only one die at a time design. It could be a semiconductor level EDA tool or a packaging tool. A lot of them are running out of bandwidth. They don't have the capability of integrating and implementing and supporting these thousands and millions of interconnect that are happening in some of these very complex packages that we see coming into the market. So what is an ideal platform? Is a platform that allows you to do your design implementation, plan for your tests, do your verification, simulation, analysis, anything such as signal integrity, power integrity, thermal analysis, and of course, by having all the extraction capabilities that you're needing to do in the same environment, using the same cockpit, so you don't have to learn different GUI interfaces. And ideally also be able to see 3D view, not just a 2D view, to know where to correct things if you need to, and really internalize viewing of trying to get an insight on where things are, where you can further optimize them. To be able to not just, again, explore, but also floor plan, route, test, everything within the same environment without having to leave to a different tool, translate, and try to figure out what would be the most optimal environment to get your job done. So auto routing, like I mentioned, auto shielding. So this is an example of a single SoC maybe connected to 2 HBM dies, stacked dies. So they require shielding. All those thousands of connections, as you see, you are able to do with the optimal tool to be able to do auto routing and auto shielding with the most density. So this would be ideal for a silicon interposer, which is traditionally done in 45 and 90 degrees angles. Whereas if you're going to the fan out, you're talking about any angle routing, teardrop, the oblong shaped devices that you have to deal with, or the gassing hole that needs to be placed. Again, you don't want to do those things manually when you have thousands of these signals that needs to be connected. You want auto routing and auto shielding, and even in the case of fan out, you want your degassing holes to be even automatically placed. Now, these are all signal connected related aspects. You have all those power and ground signals that needs to be addressed also. And imagine connecting those manually, connecting from the micro bumps, your hybrid bumps, to your C4 bumps or the copper pillars in order to connect to your package substrate. Now, we talked about a lot of the implementation aspect of it. As I highlighted, signal integrity, power integrity, thermal becomes more critical, and that needs to be done. Why need to go to a different tool to do that? Why can we define these EDA tools to have similar interfaces that can communicate together, that can share similar data models to the most efficient way of transferring data from one stage of design to another stage of design, to be able to use to do your design for testability planning, checking within the same structure, and of course be able to create an environment you can do entire design flow all the way to sign off in the same platform.
Rita?
Yes, please.
So does this single cockpit make it more difficult to mix and match tools from different EDA vendors? The assumption is all of this comes from the same vendor, and I know some companies can do that, but doesn't always work for a lot of smaller companies.
So being in OCP ODSA, and the reason I'm presenting this is a plea for a more commonly defined interfaces. That is the issue with the silo point tools, very much like you pointed out. But there are certain output formats that are very common. But what's missing is those commonalities are existing within the semiconductor world. So the GDSs, the Verilogs, the LeftDAPs, those are very standard, well-defined interfaces. But when you get into the package substrate environment, you're talking about a lot of different formats. That's the part that is missing. That is the part that is not getting integrated. So for example, I can bring the GDS from one vendor. So any of these dies can be designed by different, using different tools. But in order to fabricate those chiplets, you will create a GDS2 format or OASIS format to send it to your fab. So that format is standard. That format can be inputted to a tool like this,
right,
that would have a common platform. You could bring a LeftDAP from a whole bunch of different technology. And the beauty is, the best thing is, why can't you design a tool that would be agnostic of what format you bring in? I mean, it doesn't need to even depend on a foundry or a technology node. You could create your own because you want to explore. There's so much, if you would spend so much time upfront in your exploration phase, you would minimize all those glitches along the way of design. And of course, you can always go back if you have an environment that would allow you to go back and see what kind of decision you made based on what, and then what happens now that you know a little bit more about your design, how you can optimize it further, and what would.
I have a question, Rita.
Yes,
excuse me. I was wondering, how would the structure, how are you taking into account the information sharing at different levels of the design process of multiple actors and their legal and commercial concerns there?
I'm not following the question, but so at different phases.
I'm talking about IP. I'm talking about the chip designer. How much is he going to share with the next level that's going to do some level of integration design? Or how much you're going to share somewhere down the line when you have a test vendor, and so I mean, just understand how you, do you have some way of doing that sharing, or putting lines there if you have to share the design or parts of the
So
design?
that's a very good point. So when you're actually doing exploration phase, you don't need to know the guts of the die, right? All you are doing is you need to have access to where the bumps are, where their pitches are, whether their spaces are, and the sizes are, right? And that would allow you to do exploration from one device to another device by connecting them and saying, okay, what's the density that you need and what type of medium you need to make those connections. I mean, if it's an already defined design chiplet, for that matter, if you want to use that term. So as long as the pinouts effectively are available to you, you can do this exploration. You can create a spreadsheet and input all that information and then start using the tool. That's the beauty of it.
Well,
Now,
I'm thinking about things like, thermal, how does it behave? How does the performance behave with thermal changes, right? And so you can use that whole simulation to derate it, for example. So, there has to be levels of access, right, for different actors that can commonly look at it or submit to a design. I don't know, we've talked about information sharing as a challenge, and this is where a lot of information will reside.
Yes, exactly. So there are different levels of design, as I mentioned. There's exploration, there's design, implementation, validation. You could do a lot of those analysis upfront in your exploration. Depending on how much information you put in, that's how accurate your analysis is going to be. So yes, if you don't have a lot of detailed information, about the power of your particular devices, it's going to be very hard to have a very accurate thermal analysis. So yes, there's a next level of detail that would be needed. Again, there are different stages, and different stages of the design would need different detail levels of information in order to get your job done. But if you're just exploring to figure out which devices can I connect, what type of medium to connect, what kind of information I need, or how can I create an imaginary device before I would even decide what kind of die to design. And if I put my IPs here, there, I mean, you could be floor planning your chiplets as you're trying to floor plan your die-to-die connection, or even your package substrate design, and provide feedback. But then if you're actually actively using a device that is already designed, yes, and you're trying to integrate it and try to analyze it, those information should be available. But then the question is, because of the proprietariness, I think the chiplet provider needs to provide those necessary information. So as a standard organization, we could define what we need and tell them that, okay, these are the tools and these are the information they need. So we need to appeal to the chiplet manufacturer. That would be a requirement. You need to provide that type of information, power levels, or how your meshes are within your chip, that would give the most optimal power performance.
Rita? This is Suresh. I just wanted to chime in a little bit here. So isn't the CDX kind of trying to solve this information exchange problem or the issues and standardize that? That's one thing.
IEEE 2401 you're talking about? Sorry.
Sorry?
You mean the CDX? Yes. I apologize. Go ahead, please.
No, the CDX, I feel, is addressing the questions that Ali raised in terms of information exchange between the chiplet vendors and what types of information are required for this integration. The second aspect is the EDA flow and kind of the automation pieces. What I also wanted to draw attention for the group is actually today is the third day of the KGD workshop, but I think those presentations will be available in a couple of weeks. If some folks have not seen it, I would highly recommend, because there's yet another level of collaboration that companies like AMD and others are highlighting to enable chiplet integration from a manufacturing standpoint, then understanding overall system performance. So it's not clean division like we're thinking about it. There's a lot more into collaboration required for multi-die. I just wanted to throw it out there.
I support everything you said there, and the only thing is, obviously the big guys, this is really, really expensive with these silicon interposers, and the big guys have been doing it themselves for a few years now, and they find a way with all of this. But this would absolutely be a must if we're going to try and enable the wider ecosystem so that we can do it as a lot of smaller companies can bring their chiplets and integrate them together. So I see that this is super important. But it's a tough enough job anyway. I would focus on the the democratization of it, where lots of small players in our industry can actually partake, rather than just at the cream end. They sort themselves out with the guys that are making all the money.
Maybe we'll need targeted chiplet SIPs to do the calculation so that we can design targeted chiplet SIPs.
Maybe, yeah.
That was a joke.
So going back to the EDA world, I mean, definitely those are the type of information that we need per device in order to do the job. But the question also earlier was, how do we have an option of integrating external tools beyond just the captive tools? So Synopsys being, we already have a lot of point tools. So we can say, okay, we have the full slew, everything very tightly integrated in the same cockpit. All the capabilities are there in one. But what if the customer wants to use somebody else's, another vendor? So we actually at Synopsys, this is the 3D-IC compiler product that I have, that I manage, and we tightly integrate Ansys's tools for analysis. So for thermal analysis, to a user who's sitting in front of the cockpit in this environment, it's transparent they're using Ansys's. But they're actually using Ansys's for their thermal analysis. But the viewing, mapping, everything is done within the cockpit. They're doing their signal integrity. They do the extraction. We may be using Ansys for extraction or use our own internal tools for extraction. But the simulation analysis, looking at the eye maps, the eye diagrams, everything is done within the cockpit. You don't have to leave to a different tool to do your extraction, to do your simulations, and then come back and look at your results. Everything is done there. Same thing with the EM and IR analysis. We use Red Hawk engine, but then again, information comes in and the viewing, the results, everything, the mapping is done within the same cockpit. So the user does not have to learn a whole bunch of different GUI interfaces and get familiar on how to run the tool. That's the beauty of a single cockpit. Yes, it may be threatening about how do you integrate that, but then again, like I mentioned, the tool is capable of outputting Verilog, LeftDef, GDS. Those are the very traditional standard outputs. And you could bring the information to another tool and do your standalone verification if you want to use a standalone tool. That's no problem. Or if you're trying to co-design something with your customer who may be across the world on the other side, and you want to, instead of sending PowerPoint or spreadsheet about defining where your design stages are, you could just output a GDS or the Verilog output and then send it to your customer and get a feedback on, is this what you want? So that's the beauty of creating a platform that everything is there. And especially on the other side, if they have access to the same thing, they can do optimization and then feed it back and say, hey, I'm thinking about this. What about changing this die to another thing, or moving these pitches to bigger or smaller to get the more density? So that really concludes my presentation. I hope it created some food for thought. I think there is an interest from some of the questions that came up, but again, by no means is trying to promote one tool, but really to highlight there is a challenge in the market on the EDA side. And I think at the EDA side, the feedback, such as users, such as yourself, could benefit from to further optimize, to make the job easier in designing these chiplets or these multi-advanced packages. With that, thank you.
Rita, quick question. What the last slide you presented, does Synopsys have such a tool today, or?
Yes, we have the 3D-IC compiler that it was announced earlier this year in April. Yes, we have a single cockpit environment that does anywhere from exploration to design sign-off. And it has all the capability of SI, PI, thermal analysis, and of course, design and implementations of both for fan-out and silicon interposer.
This is completely vendor agnostic. I know you mentioned ANSYS, but does it integrate any other tools?
So right now, the tool is mainly a single platform. It's not integrating tools together. It's really a very tightly integrated capabilities within one product. We do utilize ANSYS at this point to use as an engine to do our analysis for the signal integrity, power integrity, and the thermal. In the future, we could potentially integrate other capability needs, but right now we have a partnership with ANSYS. So that's the solution we are providing.
Got it. Thank you.
Any other questions?
Thanks, Rita. This is a pretty good
Thank
deck. Will you be able to share the deck?
Yes.
Okay. Hey, Shahab, last week's deck too, would you mind emailing it out to either me or Michael?
Sure, I will.
Thank you. Any more questions for Rita? That was actually nicely done. Thanks. Okay. I'm glad you postponed it. Came out really nice. Let's see. So 1, 2, 3 quick items. Item number 1, it turns out that I was wrong and that the OCP Fall Summit is actually live and not recorded. So I'd set aside 4 of our meetings to record panel sessions. And it turns out we're going to try to run them live. What that means is we have room on our agenda in October. That's one thing. And there are a couple of items I have in mind to fill that gap. If you have anything, please let me know. Second, Ravi, I was just going to do a quick 2-minute on the Bow test chip and then hand it over to you, if that's okay.
That's fine. And I want to also introduce 2 new members who joined today's call, 2 new companies, but I'll do it after your update.
Perfect. Okay. So the Bow spec is coming along nicely. There's a lot of people contributing a lot of stuff. So we're beginning planning for a Bow test chip. Our goal is to get to a meaningful design or a meaningful program proposal by the end of Q4. So Suresh is beginning planning for that. I've talked to a few companies who expressed interest in the idea. So at some point in the next few weeks, we'll fork it out into a weekly meeting. But I think somewhere, Suresh, since we have these extra slots, I'm thinking sometime in October we can do a deeper proposal once we get more people to participate.
Yeah.
So if you have the ability and you have the time, and I'm hoping the inclination to join these weekly meetings, our first goal is really to get a credible proposal together. So if you could please reach me or Suresh, I think we're reserving a 10-minute slot at the Fall Summit. And then somewhere towards either October 23rd or 30th, really do a deep dive and get all of us on board immediately after the Bow spec is fleshed out on what a test chip would look like. So please ping me if you can join this development effort, and excuse me, the specification effort. Any questions, thoughts? Okay.
Yeah, well, Bapi, the memory one was going to be one of those discussions. Do we want to still have an internal discussion before the live get together, or do you just want to do it on the live get together?
No, I think it'd be good to have two. In a weird way, I found a repeat panel is better than the first time around. So if we do an internal discussion and then that sort of juices up the live discussion, that'll be great.
So I think I've got a couple of people interested. So as was my request, the chat from Seagate was going to try and get somebody from CXL, I think, if he's on. So I think we have enough to maybe at least get a discussion going sometime in October.
Okay,
and then,
let's aim for this slot then. I'll put October 16th tentatively.
all righty. All right,
That
I'll let
gives us
everybody know and see if I can actually get commitment there then.
Okay.
All right,
And
thank you.
Rita, thanks, Alan. You jogged my memory. I apologize. Rita, Alan, Anu, you're still up for October 9th, right?
Myself?
No,
Alan.
sorry. Rita,
No.
Rita, Leigh, Anu. I'm sorry. I meant Leigh and I said Alan. I apologize. Rita, Leigh, and Anu were like gluing together an open mic idea for design space exploration.
Yeah, I believe we're still on track.
Okay, perfect.
Yes.
Uh,
Yes. Bobby, a quick question for the fabrication effort. Is there a description or work documentation?
for the sorry, no, that's the
Fabrication.
idea. So we're getting to the point where the spec is going live. We've got more and
Okay.
more stuff being checked in. So our intent is to get the 1.0 version out by the end of this month or soon thereafter,
Okay.
and then begin the process of planning for a test chip.
Yeah. That's
And we'd like it to be a multi-company effort. So basically, the ODSA POC, and Sam was on, I wanted to say this last week, but the ODSA POC is a multi-company effort with different companies chipping in. Sam Fuller's NXP had the honor of cutting the first check for the POC, I think. So Sam, thank you.
Okay.
You're welcome. Yes, we did that.
Yeah. So now we're just going to redo the ODSA POC, but at 100x scale. That's the intent for the test chip.
Sounds good. Thank you.
So yes, Leigh, if you can, please join the planning meetings. I'll
Definitely.
include you. Okay.
Definitely, I'm interested. Yeah, sure.
Perfect. Okay. Any other quick opens before Ravi does a follow on the business ideas? Okay, Ravi, it's all yours. Do you want to share your screen? Do you want me to?
Yeah, sure. I'll share, Bapi. Thank you. But before I share, I would like to welcome two new companies who joined today's call. One is Amco Technology, and Vivek Chaudhary is on the line. Another one is JSAT, and Swami Prasad is also online. So, and these both are OSAT companies, and as we all agree that in chiplet work, packaging will play also a very important role. So we had ASE who has been joining this ODSA, but now we have more company who have shown interest.
Welcome. I'm glad you're here.
Thanks, Ravi.
Sure. I'll share my screen. Give me 1 second. You can see my screen, right?
Yep.
All right. So I also would like to thank other companies who also help and vote from last time. So I think one thing which is very clear looking at all these voting is defining what type of chiplets modularity in the industry seems to be the number one focus, at least all the companies who voted. So I think since we have that one, so I want us to take the discussion on within that what kind of chip we will be focusing on. And last week towards the end of the meeting we were having discussion around accelerator, and now on did their voting, and again their number one is different from what we were discussing. So I think as a community we would have to see if where we want to focus, because we have different market or different priority from accelerator, FPGA,
Did we lose Ravi?
I think so.
Dive in.
Ah, there he's back.
Ravi, we lost you for last 15 seconds.
Oh, I'm sorry. All right. What I was saying is we have different types of chip in mind, and different companies have different priorities. Last week we were discussing accelerator, and now based on one voting we have on which is suggesting memory. I'm saying if we can narrow down into one of these areas, once we do that, then we can drill down into the remaining focus area, because all those focus area from 2 to 4 is linked to what we decide as a community to move forward.
So let me just say what I mean by that statement there, right? So to me, it seems like the market for these types of SIPs, right? The people who are going to pay for all of this expensive stuff is, you know, high density computing. And if you want to distinguish yourself in high density computing, you say, I have the best cores for such and such workload. And so those companies are going to be the ones that own the IP around accelerating that specific workload. And then they're going to build a chiplet, you know, architecture around it using all the components they can get off the shelf, quote unquote, right? So that's why I say that's actually the driver of this market. And if we want to enable it, we should work on all the stuff around it so that, you know, Google and Tencent and whoever can concentrate on designing that core engine, right? And all the software and architectural stuff around it, you know. So that's my thought about it. But I'm the only one who voted, so somebody say something.
Did we lose Ravi again? I think so.
So actually the question for the broader community is, do we have enough data here to make some decisions and move forward, or does everybody feel that we do need more information here? Because we can definitely take whatever we have right now and converge as a community, but if somebody says, hey, you know, I need to vote and can you give me an opportunity, then this is the time to speak up. Otherwise, we will go with whatever data we have.
I feel like modularity is it, and we have to look at modularity for accelerators as a market, which kind of nicely lines up with our charter.
So yes. So modularity for accelerators. I see accelerators more as peer processors these days, and thinking from a data-centric perspective as well. So I think that's processor to processor interconnect as much as anything, be it heterogeneous processors in chiplets on a package. So I would roll accelerator, FPGA, CPU, and GPU all under one line on that whole too. So it's the interconnect between them. And then I think just to get this industry started, this chiplet game started, you know, beyond the heterogeneous processors connecting to each other on package, is I/O and memory, and it's as simple as that, in my opinion. And obviously the power and delivery, you know, the power side of it, optics is part of the I/O. The power side is literally needed everywhere. The power is a hugely complex one. How do we normalize power? So I certainly, but that sort of goes with every one of the chiplets. It's ubiquitous across the whole thing, just like the tools are in a way. So I would simply say processor to processor interconnect, memory, and I/O are the chiplet categories we need to be talking about.
Well, yes, and add CPU. General purpose code.
The CPU is just another peer processor in my mind. Peer processor, CPU, accelerator, FPGA, GPU, they're all just processors.
Yeah, okay. Sorry, somebody else was saying something. I interrupted someone. I apologize.
So I had a question. In the bottom poll 2, it talks about specific types of chiplets but shouldn't the focus be on kind of what types of systems you would enable? And the reason I asked for that is if you just focus on memory, it's going to have a certain type of interface, and the controller chip has to have the appropriate interface and so on. To expand the discussion to a little bit more on types of minimum viable systems that chiplets can enable.
Okay, on that bright note, DJ and Ravi, if he's on, I feel like Suresh pretty much hit it on the head, and that's a jumping off point for a follow-on discussion since we're out of time.
Yeah. So, Bapi, can we have another discussion on this? I don't think we have spent enough time here.
Oh, absolutely. I've
yeah.
scheduled it at the stand, and now we've got, yes. So now that we've got these slots in October, I think we should. Absolutely. I agree.
Yeah. And
Is
can
there a
we
separate
request
business group
everyone
meeting?
to?
Is there a separate business working group meeting? Is my question.
No, the point is to make these become the business working group meeting once we sort of settle on a target.
Yeah, actually, we are even willing and open to have working group meeting, but we need enough quorum so that we can be effective in the working group. And that's why we started this effort to start the quorum, and then we can launch into a working group.
Okay, we're losing people. So Rita, thank you. This was a great talk. We lost Rita too. And Ravi and DJ, thank you again. And I think we need a follow-on call on this.
DJ, I'll join a working group. I'll commit.
Okay, thank you, Ali. We'll consider you as core, and then we can formulate how to move forward this process. Thank you.
Awesome, everyone. Thank you. Have a great weekend and everything. See you next week.
Bye-bye.
Bye. Thanks, Ravi.
Thanks.